Okay, welcome back to Playing with Ray Diagrams. This time we're not going to look at a plane mirror, we're going to look at a curved mirror. Curved mirrors are more fun, that's why you tend to find them in fun houses. This particular mirror is a convex mirror, and it has a wide field of view. If I put it over here, you still see the camera. Put it over here, we see the camera. We still see the camera over there, well, a little bit. Okay, we can see the camera through a large area. That's why they use these as security mirrors in grocery stores and convenience stores and the like. They're also the kind of mirror that you have as your side mirrors on your car, where it may be printed on there, objects in mirror are closer than they appear. They're closer because they're not really that small. They're bigger than that. Now, a convex mirror, no matter how close or far you get, and I'll try to hold this properly, it keeps the image in the same orientation and it stays smaller. Okay, that is smaller than the camera would look if I use a plane mirror. If I replace this with a plane mirror, which I have one over here, and if I were to catch the camera is much, much bigger than that. And I'll keep the camera in sight here. And when I come up close to the camera, that's how big the camera looks when I'm nice and close to it. If I bring up the concave mirror, I'm sorry, I said concave again, this is convex mirror. It is still smaller, even though it's gotten larger as you get closer. Okay, now we're going to draw some ray diagrams. Now, there are some standard rays that we always draw. Now, first of all, we got to draw in our primary axis, our principal axis, our axis of symmetry. It's called lots of things. Now, I want my object to be over here, and I want this to be behind the mirror. So this has to bulge outward because it's convex, just like flexing muscles. Vex, flex, same thing. So I'm going to put my center of curvature back here. And I'm going to get a curve drawing device. And I'm going to pick this one because it goes through that square there. Now, as we showed earlier with some images, not with a video, anytime we get very far away from our axis of symmetry, this line here, we get distortion. So we never want to make a giant mirror, okay? When we played with the two-dimensional mirrors and it was all the way here, anytime we got close to being up here, it focused at a different location. But when we were down here in the middle, it always focused at the same spot. It focused the same way that a parabolic mirror does, which is a very good focusing mirror. We also discovered that the distance to the center of curvature is twice the length to the focal point. So we got to put our focal point in here. This is our center of curvature. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm sure that was a lot of fun for you to watch. Okay. Your focal point has to be half the distance to your center of curvature if you want to draw a good diagram. Now, our object is going to be out here, and it's going to be reduced, so I can draw it moderately big. And I don't need to use my ruler for that. Okay, we'll put this guy right here. He is 1, 2, 3, 4, 5, 6, 7 boxes tall, so the height of my object is a 7, and it's a positive 7. Real world in front of the mirror, virtual world behind the mirror. I have to put my hatch marks in to emphasize where is the virtual world. Okay, so Alice in Wonderland over here, Cheshire Cat this side, Grumpy Cat this side. Okay, now we have a few different rays. The first ray that we usually use is the parallel ray. The parallel ray is parallel. Well, parallel to what? Parallel to our central axis. And so I am going to draw this thing so that it comes straight in, hits my mirror. Now, parallel rays are parallel on one side. Then once they hit a mirror surface, or possibly a lens, they then go through the focal point. Okay, the focal point sometimes back here, sometimes out there. This time it's right here, so it's going to go from there through my focal point. there to there. Now the thing is, the light from this looks like it's coming out. Now this is a mirror, so it's going to bounce off. Well, that's the direction that it bounces. It bounces out there. Now if I wanted to find my my normal in order to show that the angle of incidence equals the angle of refraction, that would be straight out from the center point, because that would be radially outward. So I'm going to draw that one in here. This one is not something that you have to draw in. I'm just emphasizing a point here. And this angle is equal to that angle, and that's what always happens when we have mirrors. Now this was called our parallel ray, so I'll label that with a P. The light is coming off of my object, but it seems like it's coming out away from somewhere down here. Now the next ray that we're going to draw is the one that goes towards the center point. Now if we're aiming at the center point, we're aiming right down the barrel of the normal. So that means that not only is my light going to come in and look like it's coming from back here, it's also going to bounce back and head out in that direction. So my light is coming this way, but it looks like it's bouncing back and going in that direction. I see light that is moving outward from some location, and it looks like it's coming from right here. All right. That is our C ray, or the ray that is aimed at the center point. Now we have two other rays that we frequently use. The next one is the focal ray, the one that aims at the focal point. Now this is not going to reach the focal point because it's going to hit the mirror and do something weird. I'm going to move that down a little bit. Now, it's going to hit the mirror and then it's going to bounce. I'm not going to extend it out this way because that's not what it does. It aims at the focal point. If it hits the mirror, it's then going to leave parallel. And so it's leaving, going off in that direction. Okay, now where does it look like it came from? Well, it looks like it came from back over here. It looks like it came from here. This is where our image is going to be. Now I am going to draw one more ray just to make this complicated. Okay, now in this particular one, they're lining up great. Now they don't usually line up great. Usually you get a general range in which they look like they're crossing, and that's where you put your approximation at. Now this last one, do you notice that right here, our curved mirror seems to be perpendicular to our central axis? Isn't that the exact same thing we have for a plane mirror? That is. And so that means if I were to draw a line straight down to there, it would come down and it would hit exactly the same distance below here. 1, 2, 3, 4, 5, 6, 7. It's going to aim at that point. Now I've just made a tactical error. And the tactical error is that this last ray did not agree with everybody else. Now, coming away from there, looking like it's coming from here. Now everybody agrees, all this light seems to be coming back from this general region. Now, if I'm just making a sketch, I'm going to approximate where my rays cross. And if I'm going to be leery that a ray is wrong, I'm going to be most leery about, well, in this case, I got 3 of them that seem to cross in one point, which is really good. But I'm going to be the most leery about the rays that hit the farthest away from the central axis, because they are the ones suffering the most from spherical aberration. That's because this is a circle and not a parabola, so it doesn't focus as well if we use points that are far away from the central axis. All right, now as far as a general sketch goes, I'm just going to say that this guy is about to right here. He's about that tall. Now, a lot of us would like to make values that are better than that. But let's first of all summarize what we see here. The image is upright. Okay? The image is upright. It's not flipped upside down. Now, upright images are shown to us when our magnification is positive. And our magnification is positive when the height of our image is positive. In other words, upright. It is virtual because it's behind the mirror. Virtual means that the distance to my image is negative. It is it is smaller than this one. That means it is reduced. It is reduced, and which means that the absolute value of my magnification, I'm going to stay away from just saying my magnification is less than 1. I want absolute value because you can have negatives. It can be upside down and either reduced or enlarged. My magnification is less than 1. That's what I mean by being reduced. Lastly, the location. The distance to my image is less, or at least the absolute value of the distance to my image is less than the absolute value of my focal length. And that will always be true. Here's why it will always be true. If my object were right here, here's my parallel ray. It's going to form somewhere along this line. So it can only be from here up to here. If I put this guy way the heck out here, again, that parallel ray still defines the same area. So it can only be up to there. Okay. If I'm farther away, I expect it to be closer to the focal point. If I'm closer, I expect it to be closer to the surface and larger. But no matter what I do, it is going to be smaller. It is going to be upright, virtual, it's going to be reduced, and it is going to be closer than the focal point. We'll be back with our calculations.